So for our results, we were successful at shuttling around the corner. So to go from electrode 8, and I apologize I don't have a picture there, but to go from right here to right there, that could be accomplished almost 100% of the time. Out of 882 trials, that was successfully performed in intermediate time. To go the reverse direction, that was also that had also a high success rate. The parts of this process where we didn't have as high a success rate were when we wanted to be able to separate two ions that were in the same trap. That was difficult because, so what we do is we take two ions here, we shuttle them back to this region and split them apart. The reason that's hard is because the separation between the two ions depends on the trap strength. So what you want to do in this sort of a routine is you want to weaken your trap a lot and then bring the voltage up on the two middle electrodes so that it sort of raises the voltage up in between the ions. However, the length of these electrodes is about 400 microns. And the separation of the ions when we weaken the trap is about 50 microns. So you can see that from that ratio that it's still a difficult task to be able to bring the voltage up in between them. And that leads us to the kind of the importance of making really thin electrons in a region where you want to be able to separate ions. So here's an animation of a routine where we take two ions and we reverse their positions. Just show it again and it should run. All right, so the red ion is closer to this side. The blue ion goes around the corner. The red ion goes to the right. And then they return swapped in position. One thing that you should notice during this routine is that the red ion actually turns left before it goes right. And the reason it does that is because our layers are misaligned on the T-trap. And since they're misaligned, it's easier to turn left all the time and then shuttle straight back through that region. So the separation routine has a success rate of about 60%. And when we run this whole process right here, the total success rate is about 24%. And it's mostly limited by that separation routine as well as the recombination part of this where they come back together. So this brings me to the bulk of the research that I did, which was in microfabricated traps. As far as advantages go, microfabricated traps are nice in that there's no assembly required. And you can see that from the previous picture in that we're never able to make a right turn in the T-trap for misalignment reasons. And so if you had a microfabricated trap using photolithography, you would be able to really precisely define your vertical dimensions. And so we hope that that problem would not really be there. Secondly, you can make really small electrodes. This picture might be hard to see, but I zoomed in on the T-trap and then put a scaled figure of the gallium arsenide trap. And you can see that one electrode on the gallium arsenide, so that's one electrode, is about 1/8 of the length of or 1/7 of the length of the whole electrode in the T-trap. And that, in fact, is probably, that gallium arsenide trap can be much smaller as far as its electrode width. Another advantage is that this system has, I call it scalable, but it's nice in that you can change your photolithographic mask if you want to change the design of your trap. And so when you make a design and you realize that you need a junction region somewhere else, changing things with a photolithographic process would be much easier than remaking the whole system manually. And then lastly, the onboard filters for DC electrodes and control electronics integration. That, for a manually fabricated trap, is really difficult. You have to individually wire each of these little circuits here, and it's not a very controlled process, and it takes a long time. But for something like a semiconductor fabricated trap, all of these things could be incorporated on the chip. However, there are also several key disadvantages to microfabricated traps. One is that the material properties are not ideal. So in the manually fabricated traps, we use gold that's layered on top of ceramic, and ceramic is a really good insulator, and gold is a really good conductor. But for a semiconductor traps, the conductors consist of doped gallium arsenide or polysilicon or really thin layers of metals. And all these components have Another disadvantage to these traps is that you have restricted physical dimensions. Typically, that is most restrictive in the vertical dimension because if these traps are patterned with MBE growth or with oxide growth, the amount of material you can grow vertically is limited by system requirements. In the lateral dimensions, that is not really a key consideration because you just change your mass, but in the vertical dimension, it is. And finally, the small size of these traps, meaning the distance from the iron to the electrode, that has a negative effect on the heating, as I mentioned earlier, the motional heating of the iron. So now I'm going to go through kind of all of the traps that we've done. For completeness, I'll include also the ones that failed, and this is one that failed. And this is a single-layer gallium arsenide gold trap. We tried this early on because we were able to make it really quickly. It's only a single layer, so it didn't require some of the processing that the two-layer gallium arsenide trap had. Also, since it's a single layer, there was low capacitance to the ground, or there was low capacitance between neighboring electrodes because they don't have very much surface area between them. And also, that enabled these electrodes to withstand high voltages applied to them. And so we tested this trap by applying over 1,000 volts RF to it and applying alternating DC voltages to every other electrode. So the disadvantage of a trap like this is that it typically has low depth because there's no ground nearby. And this one didn't work. We aren't quite sure why. But it was one of the reasons we had decided all along that we were going to move towards a two-layer trap. That was our initial design. And we tried this just to see if it would work. But then the nice thing about the two-layer design is, as I showed you before, in comparison their trap strengths and depths between a single layer and a two-layer, the two-layer one is a factor of 20 stronger. So,
can you have a couple of things? But one is, why did you use silicon oxide for this? It's a better insulator.
Why didn't we use silicon oxide on a gallium arsenide?
No, just silicon with silicon oxide.
Oh, for this single layer trap?
Yeah.
Oh, that would have been a better material to use, but this was built out of the same MBE wafer that we ended up using for the two-layer structure. So, this was the...
Is there a way to do, like, in principle, let's say you have silicon, and then you have an oxide, and then you pattern gold any way you want. Now, the silicon oxide is a very good insulator. It's actually probably you can apply very large voltage.
Right.
Make any thickness you want, micron, that. But the silicon can be doped also. So you would have, it's like, it's not two layers. So you have a conducting layer.
Sure.
Would that give us help?
Yeah, and in fact, we have a substrate, or we have a wafer that has the exact same, or a very similar vertical structure to the gallium arsenide trap, but it's made out of highly doped silicon and silicon oxide layers, which were made by taking two wafers, throwing oxides on them, putting them together and annealing them, and then polishing one wafer down, and then repeating the process. So